Hello everyone, I am Dhaval from Department of Chemical Engineering, Indian Institute of Technology, Madras, India. Today I'll be presenting my work on investigation on synthetic natural gas storage in the form of gas hydrate. Basically, I'll be discussing introduction to gas hydrate, importance of natural gas economy, concept of natural gas hydrate transportation, challenges in natural gas hydrate research, experimental setup, results, ANN model, and conclusion. Talking about the gas hydrate, basically gas hydrates are formed in the presence of gas and the water at a low temperature and a moderate pressure. They convert basically gas and water convert with the help of hydrogen bond into ice-like crystalline solid, which is also known as a Clathrate hydrate. So gas hydrate has a storage 1 meter cube of gas hydrate has a storage capacity of around 164 meter cube of gas at a standard temperature and pressure in the presence of zero point 0.9 meter cube of water. So basically, there are three types of structure of a gas hydrate. Uh, Structure one hydrate is basically formed with a combination of two small cages and six large cages, which can trap methane, ethane, like medium size gas molecules. When we talk about structure 2 hydrate, it is basically formed with a combination of 16 small cages and 8 large cages, which can trap smaller size molecules like H2, N2, O2. And because here more number of the smaller cages are available, because of that reason they are preferring smaller size molecules. When we talk about structure H hydrate, this is formed basically via three cages, three small cages, two medium-sized cages, and one large cages, which can trap larger molecule with the presence of one more gas molecule. Why we need to study natural gas economy? Because natural gas has a very uh, high demand in the upcoming future, which is demonstrated by US Energy Information Administration in the current year. They studied the past data and they projected the future projections. And based on that, we can say that renewable energy will take around 40 to 50 years to overtake the demand of natural gas. So by that time, we will be reliable on natural gas fuels. For that reason, natural gas hydro transportation is now important, right? It is studied by one of the Japanese company, Mitsui and Corporation. With collaboration of Japanese government, they conceptualize the natural gas hydro transportation via ocean route, and uh, here where we can see the graph between total capex and transportation distance. From that we can understand that for low range, like if you want to transport the gas towards a low range, then pipeline gas and CNG gas is economical. If you want to transport the gas at a medium range, then natural gas hydrate is the economical one, and for longer range, LNG is the economical one. So if we compare now CIF gas cost with quantity of the gas transported, then we can understand that for a small quantity, natural gas hydrate is a better, and for large quantity, LNG is better. So now I'll be demonstrating the natural gas land transportation, which was first introduced by the same Japanese company, and basically they demonstrate the LNG transport via natural gas hydrate from the LNG base to the customer end, and for that they are doing natural gas hydrate production uh, at uh, uh, at a production base, and then they are transporting via roadways to the customer end, and then there they are regasifying it and using it. This is the in a world first natural gas hydrate plant, which was established in Chiba, and it has a 60 kg per day of capacity. And later on, they increased the capacity to 5 ton per day in Yanai. Now, what are the challenges we are facing in the gas hydrate formation? So basically, uh, gas hydrate is a gas liquid phenomena. Once the gas hydration starts, hydrates start forming at an interface, and it will form a layer which will enhance the mass transfer resistance, and hence will be having a lower rate in the further time. So how will we encountering it? So for that, there are total three approaches we are taking care. First is process intensification, in which we are using a star tank reactor, packed bed reactor, spray reactor, bubbling column, and these are the some of the pictures from our lab. But in this, there are some challenges, heat removal challenges in the spraying. In the spraying, designing of a bubbling tank is a difficult one, and etc. So the other way is a kinetic promoter. Kinetic promoter basically increase the rate of gas hydrate formation, and but they are also having one disadvantage of forming a foam. If they are forming the foam, then the foam handling is becoming a tedious work for us. So one more approach is there, which is known as a thermodynamic promoter. So a thermodynamic promoter shifts the thermodynamic equilibrium condition of the gas hydrate, and they form a more uh, they they consume more gas molecules for forming the more hydrate, and but they are also having one limitations. They are taking part in the hydrate formation process, and they are also getting consumed in it. So this is the gas hydrate experimental setup for ours. In this, we are having two-sided window reactor, which is getting stirring from the magnetic stirrer. Uh, Temperature in the reactor is maintained by the chiller unit. Once we will be having a desired temperature, then we'll be charging the gas at a desired pressure. At each 5 seconds, temperature and pressure data are collected through data acquisition system, and that are further processed in the computer system to get a mole consumption and the gas uptake data. So these are the gas uptake data and the mole consumption of kinetic hydrate promoters with respect to pure water. So here we can see like water has very low, with water we are having very low mole consumption. But if we are using the kinetic hydrate promoter, here we have used SDS and SDBS of 0.01 mole percent concentration. So we'll be having around 0.06 mole consumption, and we'll be having it will take very less amount of time. A similar graph can be observed for gas uptake. Gas uptake is nothing but moles of the natural gas uh, per mole of water. So, and if we are using the thermodynamic hydrate promoter, here we can see from our previous graph that we have achieved only around 0.06 mole consumption, right? And in this thermodynamic hydrate promoter, we are using around like we are getting around zero point 0.2 mole consumption. So it is basically increasing the thermodynamic behavior, enhancing the thermodynamic behavior of the hydrate formation. And a similar curve can be observed for the gas uptake in this also. So we have also performed a thermodynamic study using high pressure DSC, which is one of the sophisticated equipment present in our lab. Uh, This is the data we obtained from it. Basically, in this equipment, we fix the cycle of in which we are reducing the temperature from 25 degrees centigrade to minus 40 degrees centigrade, and after some time we are increasing the temperature to again 25 degrees centigrade. In this we are getting these two peaks, which the largest peak shows the crystallization process, and these three smaller peaks are basically because of hydrate formation. And when we are increasing the temperature, there is a peak, larger peak observed for ice melting, and other one peak is observed for the hydrate dissociation. The similar curve is observed for the thermodynamic hydrate promoter, which is THF, in which we are getting the higher peak, which is more intense peak, and this is because THF is taking part in the process, and which is also like very spread out. So this is evident that THF is taking part in the reactor in the process. Now we have also done the artificial neural network, which will give us an idea on how our data are behaving. So artificial neural network. So what is it? Artificial neural network is basically a method which by which we are trying to mimic the biological neural network which is present in a human body. So in our human body, basically dendrite are taking the inputs, and they are uh, transferred via axons, and the similar approach we can also use for artificial neural network for modeling the process by which we are introducing the inputs, and through the mathematical model we can get a desired output. So here in our body, just the same as our body transfers the data, the similar way we can also make different hidden layers of neurons for getting a similar kind of data which we obtained through the experiment. So here we have used a three parameter model in which we have defined time, pressure, and temperature as our parameter, and we have tried different hidden layers for getting a artificial neural network. And towards the end, we got around R square value, which is more than zero point 0.9 for both of the kinetic and the thermodynamic promoter, which is demonstrated here. So talking about the conclusions, so natural gas can be stored into the Clathrate hydrate with the help of a pure water, and it opens the enormous opportunity of safe storage and transportation of a natural gas. Thermodynamic and the kinetic growth of a natural gas hydrate has been studied, and ANN modeling was done, which is uh, used to reduce the dependency of the on the experiments. And natural gas hydrate process design will be done in the SPEN for the future perspective. These are some of the references which we have referred. And at last, I want to thank my institute, Indian Institute of Technology, Madras, for providing the research and analytical facilities. I would like to thank my faculty advisor, my research group, and my parents. Uh, and these are some of the pictures from our college. Thank you.